Hi, in this video I want to talk about hash pointers, the Merkle tree, and how these two concepts, how they work within transactions. A hash pointer is a data structure that is comprised of a pointer that points to stored information and also a cryptographic hash of that information. So in a blockchain, in every block, it points to the previous block, and also in that same block, it contains the hash of that previous block. So for example, in block one, there's a pointer that goes to block 0, and in that same block, in block 1, there's also the hash of block 0, and then this continues on into every block. So block 2 also has the pointer to block 1, and also the hash of block 1, while it's also containing, of course, the data in block 2. It's what miners use to validate and check the history of transactions, and it is a very good way to discourage any tampering of the transactions within blockchains, because if any information is changed within within a block, then the cryptographic hash of all the other blocks change, and then this way nodes will know that there has been tampering within the blockchain. So essentially, a linked list that uses hash pointers is called the blockchain. In this blockchain, we see each block containing transaction data and also the pointer and hash of the transactions within the previous block. So for example, here in block 1, there's transaction data, but then there's also a pointer linking to block 0 and also the hash of the transaction data within block 0. The same with block 2. So the block 2 has its transaction data, but it also has a pointer that relates to the previous block before it, so block 1, and also the hash of the data stored within block 1, and yet the same goes for block 3. Note that within blockchains, usually the hash pointer that it links to the last block, so in this case to block 3, is kept. And the hash pointer of block 3 not only relates to the data in block 3, but also the data in block 2 and block 1. So they're all linked, as I previously mentioned. So that way it's really hard for attackers to tamper a single block within the blockchain without letting the nodes know. So let's say an attacker tries to tamper with this blockchain, and he starts by changing the data in block 1. But by changing this data, he's also changed the hash of block 1. And that hash is located in block 2 as well as the pointer of block 1. So to do that, the attacker changes some data in block 2 to try and really cover his tracks and show the nodes that there has been no tampering with any of the transactions within this blockchain. But now, because block 3, the hash of block 2 has been changed, which is in block 3, so now the attacker would need to change the hash pointer in block 3, which he can do by changing the content in block 3. But now the tricky part for the attacker is that the hash pointer of block 3 is kept. So there is no way to really change the pointer block 3 when there's no other data and then the blockchain to change. So here, this way the nodes know that there has been tampering of the blockchain. Now I want to talk about the Merkle tree. The Merkle tree is a binary tree that is built from hash pointers. So the leaves within the Merkle tree, they're the very bottom of the Merkle tree, so the very first transactions that are hashed. And then eventually they're paired up, and then they're hashed together in pairs and into branches. And then eventually those branches are then paired up and hashed together until only the root hash is left. And this is done to make the blockchain data more efficient and also secure. So I want to now better explain how Merkle trees form by showing this Merkle tree and also providing a step-by-step guide on how these hashes are created. And so at the bottom, if you see here, we have data blocks, and then each data block is then hashed into the leaves, and then they're paired up and then hashed again. So So for example, here, so hash 0 is linked to hash 00 and hash 01. So this hash 0 here, it's a branch of these two leaves. And then the same with hash 1. It's a branch of hash 10 and hash 11. So here the branches are formed, and then eventually these two hashes, they're paired up, and then uh, one hash is created from them, and that is the root hash. Because the Merkle tree summarizes all of the transaction within just one hash, which is through this root hash, that requires very little memory or disk space, and this really helps miners in being able to verify transactions in a more secure and more efficient way. Thank you so much for watching this video. I hope you got a good understanding of how Merkle tree and hash pointers work, and also got in-depth insight into the security of transactions within a blockchain. Bye.